Hey there, how's it going? So in this video we're going to be looking at how to differentiate exponential functions. Similar to the log video, we'll start with base e and then consider other bases as well. And just a heads up, in the sequence here, I'm assuming that you've watched my previous video or you understand how to differentiate logarithmic functions. There is other ways to show the derivative of e to the x and hence any base to the power of x, but this is my preferred way. Alright, but to start, let's consider the graph of just any old exponential function. Okay, so y equals a to the x, so it could be like 2 to the x, or 3 to the x, or 5 to the x, something like that. And let's again have a look at what the gradient of the tangents look like along the function. Right, so if I draw a couple in with these red lines, a few things are apparent from this. So one, first of all, is that those gradients, those tangent lines that I drew in, all of their gradients are positive. Okay, so we're looking for the gradient function of an exponential function. We're looking for something which is always positive. Then what's happening, like as we move further to the left and right? Well, as we move further and further to right, notice that the gradient of those tangents is getting steeper and steeper, right? So, you know, if this is like a gradient of 1, that's a gradient of 2, this is maybe like a gradient of 4.5 or something, they keep on increasing. So, just like the exponential function, as you input x values, the output value on the function keeps increasing, so too does the gradient of the tangents, right? As we take on bigger and bigger x values. All right, and then what happens is we keep on moving further towards negative infinity. Well, those gradients, as we're moving right to left, are getting shallower and shallower, still staying positive, but the numbers are decreasing, but they're not going to decrease and go down into negatives because they're always going to be positive, but they are tending towards 0. So, what type of function is always positive, tends towards infinity, as x goes towards positive infinity, and tends towards 0 as x tends toward negative infinity? Well, you're looking at it right now, another exponential function. Right, so the question is it going to be this exact same exponential function, right? Or are we going to have something like a kind of shallower exponential function? Is this here going to be, is that the gradient function, or maybe something that's a bit steeper? Is this one here the gradient function? Alright, well, let's derive the rule and then it will become apparent how steep it is. So we're going to start with, I'm going to use function notation for this case, similar to how I did the use the log rules to log differentiation rules to prove the power rule in the previous video. So let's start with the function e to the x. So like I said, we'll deal with base e first. Okay, so what I want to do is take natural log of both sides. I'm going to take natural log of the left-hand side and of the right-hand side. Okay. Now over on the right, I've now got natural log of e. So log base e and a base of e are going to cancel to leave us with just x. And over here we've got natural log of f of x. Okay, and then the next thing I want to do is take the derivative of both the left hand and the right hand side. So I'm going to take the derivative with respect to x of the left hand side and the derivative with respect to x of the right hand side. Okay, so over on the right hand side, it's pretty straightforward. Derivative of x is just 1. And then what's the derivative of natural log of a function? Well, the derivative is going to be that function on the inside down on the denominator, and then its derivative up in the numerator. Okay. Now, what are we trying to do? We're trying to get an expression for the derivative of f. So we want to isolate this, so we can simply times f of x up to this side. So 1 times f of x is just f of x, okay? And then we want an expression for the derivative. F dash x or f prime x is f of x, which was our original function, e to the x. Now, I'm also going to box, to display importance, this line as well. So, the derivative of e to the power of x is e to the power of x. So that matches with what we discussed there, that we were expecting the derivative of an exponential function is another exponential function. But e was basically the special base for which it's exactly equal. It's the exact same function. It's the derivative, it's the certain base such that we have the derivative of e to the x is 1 times e to the x. So it hasn't been stretched out or compressed, okay? But different bases are going to look like this green and purple graph, where if the base is bigger than e, it's going to be steeper like this, and if the base is less than e, it's going to be a bit shallower like that. Now, what's the importance of this line here as well, that f prime x equals f? Well, it's a non-trivial function where the derivative and the function are equal. And I say non-trivial just to basically ignore 0, right? If we had the function, just constant function 0, the function 0, its derivative is also 0, but that's not really interesting, okay? Because it's a constant function and it's 0. But this is a non-zero function where its derivative is itself, right? The derivative of a power x to the n, like x5, is never going to be like x to the 5, the exact same thing, or the derivative of log of something is never going to be itself. Okay. So this is quite unique in the fact that the function e to the x differentiates to itself. This is really useful as well in what's called differential equations. So equations, right, where we've got a derivative in them. This is a very useful result because if we say had a derivative which remember represents like a rate of change, and the rate of change was proportional to just some constant number times the actual function, then we're going to get the result is that the function is going to be exponential. So this is what I mean by that. An example would be like, say we've got like a common example would be like a population of bacteria or rabbits or even humans, right? Assuming some things like, they're just kind of breeding without constraints, multiplying without other factors influencing them, that the more bacteria, rabbits, people you have, the faster the rate is. So the rate of change is proportional to the amount at a certain given time. So those kind of contexts called exponential growth, and also the reverse is decay, like radioactive decay, when done kind of properly mathematically, are a differential equation which will end up using this result. But anyway, that'll be covered in a later video where I start looking at some applications. All right, so just let's maybe do a couple of basic examples, just practicing using this rule. Okay, let's say we've got this function 4e to the 3x. So what's its derivative? Okay, well, since we've got a constant multiplied by the function, we're going to have that constant multiplying whatever the derivative is. Then e to the x, right? E to the x differentiates to e to the x. Now, since we have a function of x, 3x, not exactly x, but using the chain rule, we can kind of imagine like this is like the brackets or parentheses up there that, like, remember with like the power rule, we'd have something inside some brackets to the 7, and then we'd still apply the power rule, bring the 7 down, subtract 1 from the power. We'd apply the power rule to the brackets and then multiply by the derivative of the brackets. So here, e to a function of x is going to differentiate to exactly itself, and then we're going to times by the derivative there, the derivative of 3x being just 3. And we can just obviously simplify 4 times 3 is 12. Okay, so let's say we've got this function, e to the x squared plus 5, and we want to find its derivative. Its derivative is going to be e to a function of x is going to differentiate precisely to itself. Okay, and then we're going to multiply by the derivative of the brackets using the chain rule, so we're going to multiply that by the derivative of x squared plus 5 is 2x. Alright, x squared e to the 2x, so in here we've got, implicitly in there, there's a multiplication, so we've got a product of two functions, so we want to use the product rule, of course. So I would normally do this off to the side, but in terms of space, I'll just go down because I want that for other stuff. So let's write out each of our products, x squared and e to the 2x, and then we've got these two little mini differentiation problems to do. So the derivative of x squared, bring the power down, subtract 1 from the power, x to the 1 is of course just x, and then e to the 2x, so e to the x differentiate with, even if there's other stuff to do with the x, is going to differentiate to itself, and times by the derivative of 2x is 2. So now the product rule, we need to times each of these, and I'm going to times that one by that one first for the same habit, same order and direction as the quotient rule, but we're using the product rule, which is u dash v plus v dash u. So we have expressions for all 4 of these, so we just need to chuck them in now, right? So u dash will be 2x v e to the 2x plus v dash 2e to the 2x times x squared. And then we can just simplify that because we've got common factors of 2, x e to the 2x. Outside of that, looks like the exact same thing, so 1 lot of that plus x lots of that. Alright, so there's just using the rule, and then, using our existing rules, which are now part of our toolkit, but we also know how to differentiate exponential functions, base e only. Alright, what about if we just had any other base, right? So like 7 or 13 or whatever, right? Well, let's consider that. y equals some other base to the power of x. So what we're going to do is manipulate this so that it has a base of e, because then if it has a base of e, then we can do the rule for e to the x. All right. So here's a little trick. Right, is we can raise e to the power of natural log of something, and e to the natural log base e, are going to cancel out and give us a to the x, right? So this would just be like, because these are inverse functions, they're going to reverse each other to just leave you this. Just like if I had a to the x and I said plus 2 and minus 2, I had a to the x and said let's times it by 3 and divide it by 3 or something, right? If I take the natural, like take log of any base, like log base 5 of it, and then raise that all to a base of 5, that's going to cancel, okay? And likewise for a base of e and a log base e. Of course, that's chosen, as I said, because we know the rule for e to the x. All right, using our log laws, we can pull this x here out the front of the logarithm up there in the power of e. And so we've got e to the x natural log of a. Okay, so this is just rewriting a little change of base you can do with exponentials. And we've chosen this specifically because if I block out visually natural log of a, well, what does e to the x differentiate to? E to the x. What do we do with natural log of a? Well, a is we're just thinking of some other base, like some number, right? Like 4. Okay, well, natural log of 4 is just a number. So just like we can do e to this function of x, x times some number, and like we times by the 3, pull that down. Or we times by, say here, the 2 and pull that down. We can do the same thing here and take the derivative by doing itself, and then times by the derivative of this using the chain rule. Natural log of a. And so we get that if y equals a to the x, we're going to have natural log of a times by, well, e to the x natural log of a is this expression, which was this, which was originally back here to a to the x. Okay, so this is going to be our rule to differentiate exponential functions where the base isn't e. All right. So just bringing that back up to here, you could, for example, check what I said about whether the base is bigger or smaller than e. Remember, e is like computationally find it to be about 2.718, 2845. I don't know. Just double check it in the calculator. So let's say the base was 2 to the x will differentiate to itself, but then we've got to multiply it by 2 to the x by natural log of 2. And if you compute natural log of 2, you should get, I think from memory, it's about 0.69 or so. And so that will be 2 to the x will differentiate. The gradient function will be like this purple line here. If you do, say, 3 to the x, that'll differentiate to, just like e to the x differentiates to itself, an exponential function differentiates to itself, but just if the base isn't e, we've got to also times by natural log of the base. So 3 to the x differentiates to itself, 3 to the x, but we've got to multiply by natural log of 3, which again, I think off the top of my head, if you put in your calculator, will be about 1.1. So that will be something like, kind of like if this was 3 to the x, then the green line here would be our gradient function, right? A bit steeper. Okay, so let's do a couple of examples using this. That doesn't look nice. Let's be clearer. Okay, so Okay, let's say we want to differentiate this. Y equals 2 to the x plus 1. So if we want to differentiate this function, just like e to the x differentiates to itself precisely, an exponential function differentiates to itself, right? And since we've got a function of x up in the exponent, that's going to stay there. 2 to the x plus 1 is going to differentiate to itself. But since the base isn't e, we have to multiply it by natural log of the base. So natural log of 2. Here I'm just writing it in brackets, just so you know I'm saying natural log of 2 times this, not natural log of, if I didn't write that, it might look like natural log of 22x plus 1. Then we have to use the chain rule and multiply it by the derivative of x plus 1 up here, which is 1, but of course multiplied by 1 is itself, but it's good to still, of course, think about that. Alrighty. Okay, so here we're going to have to use the chain rule because we've got some function of x here, all raised to the power of 4. So what we can do is whatever is here, this function of x raised to the power of 4, right? We can do the power rule, bring the 4 down, subtract 1 from the power, and then what's going to be in there? Still the same function, 5 to the x plus x all squared. But then because of the chain rule, we have to multiply by the derivative of the brackets in here. So what's the derivative of this function inside our function? Well, the derivative of 5 to the x is the derivative of an exponential is itself. But because the base isn't e, we've also got a times by natural log of the base. So times by natural log of 5. And then inside there as well. So the derivative of 5 to the x plus x squared will be the derivative of this plus the derivative of x squared, which is hopefully by now pretty obvious, 2x. There's not really much we can do with that from there. Alrighty, so hopefully you've been catching the way I've been verbalizing it, that the derivative of an exponential function is itself that exact same exponential function, even with whatever function's up in the top. Of course, like any function, we've got to apply the chain rule. And then the extra little tidbit is if the base isn't e, then we need to multiply by natural log of the base. Alright, even though this is my preferred way of doing it, if you're still sticking around, I'm not going to say catch you later yet, because I just want to show as well another way to find the derivative of e to the x. And this would be like maybe how you would do it if you didn't do it the way I've sequenced this. And so you did this before doing logs, which is how we do it in the New South Wales syllabus, because it's a year 11 thing we have to teach before the year 12, the logs and that. So this isn't my personal preferred way because like I made the commentary in the logs video, I prefer using logs first, using the established definition of e as the continually compounding. And then now we get, once we know how to differentiate logs, we get this result pretty nicely, just like we also use it to get the power rule result. So instead, if we had y equals a to the x, and we didn't know this log differentiation rule, then we'd probably try by first principles. So we'd say y dash equals the limit as h goes to 0 of input x plus h into the function minus the original function all over h. Alright, now up in the numerator here, this left-hand term, because we've got a plus in the power, we can split that back out into two terms being multiplied. right? So we've got limit as h goes to 0 of a to the x, a to the h, right? Because if you think going back from this line back up to this one, multiplying with the same base, you would x plus h add the powers. All right, now we've got a to the x is a common factor in the numerator. Now, just like when we had a constant multiple of a function like k, and we could pull that out because it had nothing to do with h, and also I think in proof of the product rule, this a to the x here doesn't have anything to do with h, so we can pull that out. Alright, so by first principles, the derivative of a to the power of x is a to the power of x times this limit expression here. Okay, so I guess the obvious question then is like, what's this limit expression here? So how I'd normally teach this would be, well, I'd use something like GeoGebra or Desmos and figure this out computationally. That if we had, say, a base of 2 and you put in 2 to the, I mean, you'd have to write like x rather than h, I think is what I do in GeoGebra. I can't remember if Desmos likes using other input variables. But say like you put a to the x minus 1 all over x, and then if you're using, say, when a is 2, you can put 2 to the x minus 1 all over x, and then look at the y-intercept on that, well, where you're not going to have a y-intercept because you can't put you can't input h into the denominator, but you can visually see what it is, and then you could say that for the value of base of 2 to the x would be timesing by about 0.69, I think it was. Likewise, 3 to the x would be about, you'd get this bit here would be around about 1.1. So if you set up a slider for a, so you say like a is your slider, so I suggest have a go at doing this yourself. In GeoGebra, you can go set up a slider a and say whatever a is to the x minus 1 all over x, and then if you move the slider and keep changing the increments so that you can get like a closer level of precision, you can see that this bit here is going to become the limit, right, where you're looking kind of basically where the y-intercept would be on the graph. You look, you keep changing the slider, and when a gets to 2.7 a1a, this whole bit here evaluates to 1. So basically E, another definition of E, rather than the continuous compounding one, is that E is the special number such that this limit expression here equals 1 when you use E for the base, right? And we can see, since we've actually got this other derivation over here, y equals a to the x differentiates to a to the x times natural log of a to the x differentiates to a to the x times something, y equals a to the x, also legitimate mathematical steps, the derivative equals a to the x times something here. So if a to the x differentiates to a to the x times something, then these two somethings here are actually equal. Right, and so you can see as well, like if you put e in there, natural log of e is 1 times e to the x, which is just e to the x differentiating to e to the x. So like I said, not my preferred method, because then you have to like use a secondary computation to define e, which is kind of suboptimal in my mind, given you can define E another way that comes up in another algebraic context, and then once we use that definition for E, get the derivative of a log function, and once we've got log function, do that first. Now, the other thing though is if you did learn this first, that if you learned e to the y equals e to the x differentiates to e to the x before you did log differentiation, then you can get the rule for log differentiation pretty easy once you've already established that fact. Just like this was fairly simple to get the, I think anyway, this rule based on having the log rule first. So if we wanted to, let's pretend we didn't know that the derivative of natural log of x is 1 on x, then what we could do is say, all right, I want to know how to differentiate this. How am I going to differentiate this? Well, I'm going to take e to both sides. E to the left-hand side equals e to the power of the right-hand side. Over here on the right, e and log base e cancel. So I've got e to the y equals just x. Then if I, like I did over here as well, I want to take the derivative with respect to x here. So I'm going to have e to the y equals x, running out of space. And I want to take the derivative with respect to x of the left-hand side, and therefore I'll have to do it to the right-hand side. Right-hand side again, that's pretty straightforward one. And then we've got the derivative of e with respect to x of e to the y, and remember y is originally natural log of x, so a function of x. Well, just like 2 to the x is a function of x, and the derivative of e to, if like 2 to the x was y, right, we'd have e to the y and times by, well, what's 2? The derivative of y, y dash. So if we do this here, we're going to have e to some function of x, y is a function of x, differentiates to itself times by the derivative of that function up there. We want to isolate and find the derivative, y dash. So let's continue up here. So how are we going to isolate that? We're going to divide both sides by e to the y. So y dash equals 1 on e to the y. And what was e to the y? Well, back at this line here, e to the y was equal to x. So y dash equals 1 on x. So that would be if you learned how to differentiate exponential functions first, used a second definition of computing what e is, and then once you've established that fact, you can establish that, this looks a bit messy, but remember this was originally y equals natural log of x differentiates to 1 on x. Alright, so hopefully that was a bit interesting, and that's the way I have to teach it in class. Got to teach this first, but Nessa, give me power, let me restructure the syllabus and do this. Anyway, that's it, so catch you later.